Okay, so welcome everyone to our workshop on active matter. And I'm very pleased to introduce you to Professor Thomas Ihle. If I'm not mistaken, he did his diploma in the University of Leipzig. Then he did his PhD in Aachen. And since then, he has worked in several places. Right now, he's working as a professor at the University of Greifswald, and I think he will have a very, very interesting talk today. So let's give him the time to speak. Thank you very much.
Yeah, thank you, Tosha, for the nice introduction. And first, I would like to thank you and Andreas Deutsch for giving me this chance to give a talk here. So what I'm going to talk about is basically what we did in the last few years and trying to do a response theory for active particle systems as a way to get transport coefficients quickly and efficiently. Yeah, this was done in collaboration with Arash Nico Bashman from the University of Mainz, who did most of the computer simulations, and Rüdiger Kirsten, who is a postdoc here with me in Greifswald. Okay, so active matter, I don't need to introduce that to you. You have self-driven units that constantly exchange energy and momentum with the environment, and as such, it leads to non-equilibrium behavior. And what I will focus on is to consider such a field of such self-driven units and describe it as a fluid by hydrodynamic equations. And the question is, how do we get the transport coefficients for these hydrodynamic equations? Okay, so my goal today will be to derive expressions for the transport coefficients for these active fluids and directly getting them from microscopic interactions of the underlying model. And a second topic where I don't have time to talk about is how to measure actually these transport coefficients in agent-based computer simulations and how they compare to the theoretical predictions. All right. Yeah, so first I will mostly focus on one of the simplest models of active matter, the so-called Mischiek model, where you have point-like particles. So the particles have zero volume and they have simple alignment interactions. But these ideas about the response theory can be generalized to other models. That's just the first one I started with. And it's many people see it as a toy model because it's still relatively far from reality, but it still has not a complete quantitative theory. And for instance, last year, my postdoc, Rüdiger Kirsten, he discovered a new phase in this model, even though it has been studied extensively since 1995. So he found the cross-C phase in addition to what existed or was the polar liquid or Turner 2 phase, a disordered liquid and traveling bands, and he just found this additional phase. But I won't have time to talk much about it. It just looks like what it's like the name says. It's a cross-C of waves crossing each other at a particular angle. Okay. So just for those who don't know exactly the model, I will introduce the standard Mischiek model. Here from this famous publication in '95, Thomas Mischiek introduced it. I think it has now 6,000 citations. So it's a two-dimensional model. We have particles which go with a constant speed v0. And so the velocity is described just by this angle theta n. It's the angle of the velocity vector of the particle n with respect to some axis. And then we have multi-body interactions where particles align to the mean flying directions of the neighbors plus some noise. And here are the two interaction rules. The first one is just an update of the position vector xn, that you just add a velocity vn of that particle multiplied by a time step tau. And the time step tau here doesn't have to be small. It's an explicit parameter of the model. And then in a collision step, the direction of the particles, I mean the velocity, vector changes, and you take the average angle theta bar of all the particles in a circle around the focal particle, and then you add some noise. So that theta bar is the mean angle. So here in that picture, the yellow particle is the one we are focusing on. Then you have a circle of radius r, that's the yellow circle. And then you look how many particles are within that range, and you find in this case 3 other particles. And then you add the velocity vectors of all these 4 vectors together. It's a long vector going this way. And that gives you the mean angle. So that's the theta bar is the angle of that long vector. And then you update the, you obtain the new angle. Yeah, and the Cn is a random number, which is equally distributed between 2 values. And theta, eta here is the strength of the noise, which is an additional parameter of the model. Okay, so that's for those who haven't seen that yet. We also worked on the Vshape-like model with continuous time. So that's a stochastic differential equation which has pairwise additive interactions. And that's in some sense easier because it leads to a traditional description by a Fokker-Planck equation. And here are the equations. So here you have differential equation, not just difference equations. So the this x dot, the time derivative of the vector x, is just given by the velocity. And then the angle changes, like you have theta dot. The angular change is given by the sum of the sines of the particle I, of the angle of particle I, and the difference to the angle theta j of another particle in that interaction range. I won't talk about this continuous time model in this talk anymore. I just wanted to mention that we have done extensive work also on this model, also with response theory. Yeah. Anyway, so if you take it, we go back to the standard Vshape model where you have that discrete time step and multi-particle interactions, and you just throw everything in a small system, and you do an agent-based simulation. And then what you observe is that it's something like a phase transition in a small system where we have a polar order parameter, omega, which is the sum of all the velocity vectors normalized by the number of the particles and the velocity. And then at small noise, you get a large polar order, and then you have something like a transition here, which looks like a smooth transition at a noise value around 4. And then you have a disordered system where the order parameter is very small. Okay, that's picture changes if you go to a large systems, and this transition becomes discontinuous, and you see the traveling waves. But again, this is just a short snapshot to show you what you see if you start simulating this model. All right. So next I want to discuss some important length scales to understand the Vshape model. The first one is the interaction radius r. It's just the radius of that circle, so where you find your neighbors. And then you have a so-called ballistic length, also called mean free path, which is just the distance a particle travels within the time step tau. And here's an example. We have small ballistic length, and that's kind of a physical regime, because these particles, they travel only a short distance. And physical is, you can see that in a way that if these particles would be like birds or fish, then they would travel a little bit, and then they would start look around and see where to go and whether to avoid other particles or not. And if the travel regime, if this lambda is large, they travel a lot, and so they would actually run through each other or passing each other and not noticing each other. In that sense, it's more unphysical. But that's the regime where the approximation, which I want to use later, is actually valid. So we can't really do much quantitative work in the small lambda regime. Anyway, so the starting point for all the theories I worked with for this model is evolution equation for a Markov chain, and that's basically a hopping and phase space. So A and B are microscopic states of the entire system, and they are given by the positions of all the particles. That means their x and y position coordinates, and also the flying angle. And so this, if you know this state A, then you know everything about the system. Okay, and then you have an evolution equation, which tells you how the probability density to be in a state A at time t evolves in time. And so you take this probability density P, function of A and T, and multiply it by a transition probability, which tells you how to get from state A to B, I mean, with what probability. And then you sum over all possibilities over all states A. And then you get state B, the probability to be in state B at the next time step, t plus tau. And that looks like an extremely simple equation, but all the physics, is hidden in this transition probability, which is quite nasty. Here, let's have a first glance at it. It's basically a probability of delta functions. They're not actually delta functions, they're periodically continued delta functions because the angle is periodic with a period 2 pi. But let's just for now just see them as delta functions. And what's in here as the argument in the delta functions is the collision rule. So that what's in here is only 0 if the collision rule is fulfilled. That means that the new angle theta is equal to the average angle plus the noise. And then you have to integrate over the distribution of the noise. I mean, you have for every particle there's a different noise. That's like Ci, and that has to be integrated over that rectangular probability distribution. Anyway, so this is the structure of the theory, how we start. The problem is that we have now an exact equation for the n-particle probability distribution, and that has just too much information and cannot be treated directly. And you have to reduce it. And one way to do that is to reduce it to an infinite hierarchy of 1, 2, 3, and 4 particle distribution functions. That's called the BBJKY hierarchy. But we won't go into these sophisticated theories. We just take the first hierarchy equation and then use the so-called molecular chaos approximation to close that hierarchy. And then we end up with the so-called one particle distribution function. So that f as the function which will show up in the equation we actually work with. And it's just proportional to the probability density to find any particle at a particular position x, which points in the angle in the direction theta at a particular time t. Okay, and how to get that? Well, as I said, you do the molecular chaos assumption. It means you factorize on the right-hand side of the equation that n-particle probability distribution P of A. So you write as a product of one particle distributions. And if you do that, you implicitly assume that these particles are statistically independent at all times, which in the Vshape model you can achieve if you take a very large time step or very large noise. Then this can be that's approximately okay. And then you integrate out all the particles except one, and then that gives an equation for this function f. And that's a mean field treatment. It's an effective one particle picture because you get just one particle which feels an effective field, which describes then the average effect of all the ignored particles, the ones you integrated over. And that schematically, that kinetic equation looks like this. It's like a discrete Boltzmann equation in discrete time. So we have f at a time t plus tau for a particular angle theta and particular position. But here you have a little offset, which comes from the streaming, from the flying of the particles. And then you have on the right-hand side, a very complicated collision operator, which is an integral operator. So it's nonlinear and non-local, has basically all the ugliness you can imagine. And it can be schematically represented as a sum of a one particle, a two particle, and a three particle, and so on operator, which means that C1, for instance, describes the situation where a particle doesn't have a neighbor. And C2 is the case where particle has one neighbor, so you have a product of two of these f functions, and C3 would be the case where you have 3 neighbors, like in this picture here. Okay, and you have, in principle, you can have all the particles being the neighbor of one particle. It's very unlikely, but it's still possible because these particles are point particles. Yeah, and then many years ago, Turner and Tu proposed for the dynamics, proposed the Turner 2 equations, which are hydrodynamic equations for the momentum, for the density, particle density rho. That's basically continuity equation. And then another Stokes-like equation, also called momentum equation, for the average velocity u. And these b indices are just the components in space, so it's x or y. And then there's many terms which are different from the Stokes equation of a regular fluid. And I will just focus on these two green, circled terms. This one is just a simple growth term. So the momentum is not conserved. If this prefactor mu is non-zero, it just can grow or go down. Okay, 5 minutes remaining. Yeah. So, and here the second term is the viscous term. It has this second gradient of the velocity. And the goal now is to calculate these two coefficients in front of these terms. And this can be done in a Chapman-Enskog expansion, which is very tedious. And I will not go into details. I mean, we did it, but it was really a pain and it's very complicated. It has a lot of technical problems or issues we had to solve, like that time derivative. There's a set of time derivatives you have to introduce, but in our case, they didn't commute. So it's not really a time derivative. And also the scaling you have to do in this analysis is kind of ad hoc, and it's just justified by the outcome. And anyway, so there's all types of issues here, and we wanted to circumvent this whole expansion. And here are some results of this theory, which I won't have time to talk about. And yeah, now we come to this response theory. And the idea was to interrogate a system by recalling the response to some properly designed external perturbances. Normally, the motivation was, okay, what is the effect of a predator on a flock of birds, or how does the system change if the environment suddenly changes in time, and how does information propagate through that through a swarm of these animals, of these objects. But here we just take this idea and we just use it as a mathematical tool to derive transport coefficients. So what we do is a combination of response theory and kinetic theory. And of this way, we circumvent the Chapman-Enskog expansion. There is no free lunch here. That means in the Chapman-Enskog expansion, you get all the terms in the hydrodynamic theory, all the transport coefficients at once, but it's a huge, horrible calculation, which in practice can only be done to a certain order in the small expansion parameter. But here, calculations are much nicer and shorter, but the price is we only get 1 or 2 transport coefficients at once, and if we want more, then we have to change the configuration of the external field and go into a different calculation. And the advantage of this approach is that we get information on short length and time scales, just as memory kernels, and we can also find the wave vector dependence of viscosities and other transport coefficients. This is something very tedious to get in Chapman-Enskog. Okay, this is not published yet. We are about to writing it up. Okay, so just since I don't have too much time, is the main idea, how do we include external forces in the Vshape model? The thing is that the velocity, the speed of the particles cannot change. They can also only rotate the velocity vectors. The vectors cannot, get longer. There's no. So, and then the idea was that we had this intuition that particles should get oriented into the direction of the field. That's the idea of this external field. And so we just modify the average angle. So normally the average angle theta bar is just the argument of the vector L. And the vector L is the sum of all the velocity vectors. That gives you that mean direction. But now if you add something to this L, this vector L, you get now an average angle which is biased towards the direction of the new field, the external field H. And that's the whole idea. And this field H can depend now on space and time. And here's a way actually to express that average angle as the one in terms of the strength of the external field. We can do that for small field strength, but also for very large field strength. We get these two formulas, and then we did that with complex calculus, and I don't have time to go into that. And here I just want to discuss the main forces we investigated. So we looked at an homogeneous but time-dependent force in order to investigate memory effects and critical exponents. So the field points in the x direction, but it has the same magnitude everywhere. So particles basically get biased to fly into the x direction. Then we tried a transversal force. So here the force still looks in the x direction, but it's modulated in the y direction. So the wave vector goes perpendicular to the bias direction. That's why it's called transverse. And then we investigated a cosine modulation as a function of height of this field. And then we found the shear viscosity and how it depends on wave number. And then we can also look at a longitudinal force, or we did look at a longitudinal force. So where the force points in the y direction, but it also changes its strength in the same direction. So that's a longitudinal perturbation, and there we were able to derive the speed of sound and how the speed of sound depends on the wave number of the perturbation. Okay, my time is almost up. I just wanted to show you quickly that this whole theory, kinetic theory approach we use doesn't change much. This is actually the collision kernel in full detail. What you have to focus on is just that theta bar in here. It's the average angle, which is inside the delta function. That's now modified by the external field. So we just use the expression from this expression here and plug it in there, and then we just keep the term linear and h because we want to first do a linear response theory. But we can also do a nonlinear response. That's no problem here. It's just mathematically involved. Anyway, and then we had certain expectations. For instance, that the mean velocity should be proportional to the imposed field in the linear response regime, so that the mean velocity in the disordered phase you get should just be linear in the should scale linearly with the field strength. And then also, if you go directly at the phase transition between ordered and disordered state, and since we do mean field theory, we should get critical exponents, which are given by mean field theory. And that's actually what we found, that the mean value of u is not linear, doesn't grow linear in h anymore, but it has now this exponent 1/3, and that's the well-known critical exponent, known from, for instance, magnetic fields. Yeah. Okay, and then there's technical things how to do that. We have to go in angular Fourier space and then derive a hierarchy of equations for these different angular modes. That's what we do for homogeneous field. That looks quite horrible. I want to skip that. And then if we have an inhomogeneous field like transverse perturbation, we have to do a spatial and angular, so a double Fourier transform. And then we still get a hierarchy of mode equations, and then we only keep the terms which are linear in the external field. And anyway, if you do all that, in the end, you get a response of the first mode that's basically proportional to the mean velocity. And then the mode Q, which is the wave number of the imposed perturbation. You get such an expression which contains a lot of Bessel functions, but you can expand these Bessel functions for small wave vector, and then you get this expression. And from that, you can read off, you compare that to what you expect from the Turner 2 theory, and it has the same form, and then you can recognize that coefficient in front of k square, in front of wave vector square, must be the viscosity, and this upper term here must be the so-called momentum amplification factor. And then you look at that and you see, we saw that it agrees perfectly with the result from earlier from the Chapman-Enskog expansion. But the thing is, we can now look for the wave vector dependence of this viscosity. So here, if the mean free path is large, you get that the viscosity increases slightly with the wave number. And then in the other case, if the mean free path is very small, you get a strong decrease of the viscosity. And if you only do numerics in this range here, so that if you have a relatively small systems, you can go to really small wave vectors, you would get the false impression that the viscosity is diverging if you go to k equals 0. If you just interpolate this curve to k equals 0, it looks like it's diverging, but it's not. It's just an effect of the strong wave number dependence of the viscosity. Anyway, so I will come to the conclusions. So I showed you briefly a kinetic theory for the standard Mischiek model, which started from the full phase space description. And then we did a mean field approximation and proposed a combination of response and kinetic theory. So the new thing is we did response theory at the level of the kinetic theory. And so we didn't have to go to hydrodynamics, which involves all types of difficult approximation like gradient expansion. We just started with the response in the kinetic theory and then could get transport coefficients directly. Okay, that would be all. Thank you.
Thank you very much for your very interesting talk. Right now we have 4 minutes for questions. So does anyone have a question?
So I have a question, Thomas. Thanks a lot. You understand me?
Yeah, well, very well.
Yeah, okay. So you derived your nice methodology for the Vshape model, which one can view as a kind of ferromagnetic interaction model. Could you apply the methodology also to, for example, a pneumatic liquid crystal-like model?
Yes. Yeah, in that case, I probably would also look at a different type of field, a field which is also pneumatic. So the particle is not just biased in one direction, but can also be biased in the other direction to get more interesting transport coefficients. But I think that would be an interesting extension. And we extended it also to other models like with continuous dynamics, and also the different interactions, also the metric-free topological Vshape model we looked at. Okay. So it's pretty versatile.
Thanks a lot.
Okay, Fernando is asking a question, I think.
Hi.
Hello.
Hello. So I have a question. First, I mean, the way you wrote it I was interested in particular on the part I didn't know, which is the response, which you formulated in a way that somehow reminds me of the way we were thinking of quench disorder and so on. But now, I mean, that's only, I mean, looks similar. You have a field and may depend on the position, or, I mean, and as well as, I mean, may vary in time. Now, my question is, if you have that, I saw that if I assume that the system is driven, which is the case, if you have a field, suppose you have an homogeneous field, you should expect fluctuations to act in a very different way, right? And for example, yeah, I mean, everything has to be changed because of that external field. And I mean, I don't know, I was expecting you to say something about that, because now I can go to a regime where I may suppress or make it very small, the interaction among the particles. And if I'm able to tune that stuff, I should move from, I mean, something where the field emerges because of the interaction among the particles to something that is driven, right? So, and there I should observe things that are very different.
Also, you mean that what I measure, let's say the viscosity in this response wouldn't be the same I would get in a situation where I don't have the external field, or
Yeah, something basically what I'm trying to say is that I think there is two levels. I mean, I can go to a limit where my system, suppose I have a system that is driven. There is no interaction as in the Vshape. So I have all properties, fluctuations, and so on should correspond to my driven system, and that's it. The other limit that you can explore is the one where the external field is not present. And then you have things become very different because now the system will spontaneously break the symmetry and so on. So fluctuations will be of that kind of a system, well, the standard things that we know from the Vshape. But then now, if you have the external field at some point, you may basically interpolate between this driven system and something where the dynamics is emergent dynamics, like in the Vshape. And then I guess that should be also present in the equations.
Yeah. I mean, the thing is, I have a pretty drastic approximation made here at that mean field factorization. And also, I only look at very small fields. So, so that I try to not disturb the system, just a tiny bit to study the response. But it's true.
Yeah, let me say the other way around. What you did is you assume you were a Vshape and you perturb it that way, because now you can do the opposite. You can assume that you have a driven system. This is what I'm saying. You have a driven system and the perturbation is the interaction among the particles. Or you can assume I have a Vshape and I put the field. You see how I can place myself and the other.
Yeah, all right. Yeah, in this direction, I haven't thought yet, but that's certainly something. I should look at. For now, it was just a tool. I mean, we only looked at in that regime where there's disorder, so there is no spontaneous symmetry breaking. We just moved. And the maximum we did, we just went to this transition point, which is mean field, so it's continuous here. I guess that's all I can say to your question.
Okay, thank you.
Okay, well, thank you very much for your questions. I think we can discuss further during the break. And I think we should continue now with our next speaker. That's okay with you. Okay, well, thank you very much. Now we will continue with Reyes. So she is a physics student at the Faculty of Sciences, the National Autonomous University of Mexico. And she's my student, so she's going to present her thesis work. Okay.
Okay, thank you very much. I'll share my screen now. Here it is. So, hi, my name is María del Reyes Ortiz. I'm a student, a physics student at the Faculty of Science. And well, today I will be talking about the field of view effects on collective migration. So, first of all, our aim in this research is to create a model, a more realistic model, to explain how animals migrate, and we will use cellular automaton for this aim. So in our case, we will use specifically an LGCA cellular automaton. In this case of automaton, we have a state space that is related to the lattice geometry, and here we can define some velocity channels, which are basically vectors that point to the nearest neighbors of any of the nodes in the lattice. And in each node, we can also define some rest channels. We can see the node capacity and the total number of particles that we have in each node. So for example, in this figure, you can see that we have 6 velocity channels, 1 rest channel, and we only have 2 particles that are here painted in gray in the circles. So in an LGCA cellular automaton, the dynamics is defined basically by a local stochastic transition rule followed by a deterministic propagation step. And this leads to transport dynamics. So as you can see in this figure, we have our lattice and some of our nodes in which we have particles. So when the interaction happens, particles move to some other channels. They change in the interaction neighborhood. And then we have migration, in which particles follow their velocity channel to the next node in the lattice. So this is some of the concepts that we will be using in our work. Now we will see our methods. So in this case, we will use a general transition probability given by a Boltzmann probability distribution. That is our first equation. And we will consider two different interactions. We will consider the ferromagnetic interaction and the liquid crystal interaction. To consider both of these probabilities, transition probabilities, we consider that there is a stochastic independence between all of the velocity channels. So that's why we can write them in this way. And we consider all of the 6 different channels in each of the nodes. Now, as you could see in the previous slide, our model only considers interactions between neighbors, but it's not really realistic to think that all neighbors have the same influence in a particle. So that's why we would like to introduce a new parameter that's vision. This new parameter, we will introduce it with a von Mises probability distribution that's given by the equation number 1. This is a discrete von Mises probability distribution where we will only consider the 6 angles of the 6 different velocity channels. And as you can see in our graphs, sigma will be our vision parameter. And when sigma equals 0, it means that you can see all over the space. You have a complete, a wide range of field of view. But as sigma starts to increase and it starts to go up, that field of view starts to go down, to diminish. So you could only see in front of you. So this is how we will model our field of view. Now, to introduce this to our model, as I already said, we will also make some considerations, some approximations. First of all, we make a mean field approximation in which we basically approximate the state of a particle with the mean state generated by the neighboring particles. So here you can see that here we have the occupation of channel I at 10K, and we have the mean of these occupations, and we define that way our one particle distribution functions. And we will also make another approximation that is the low density, where we will only consider that there is a maximum of 1 particle per each node, no more particles in each node. So doing both approximations, we can get our final transition probabilities given by equations 2 and 3. Here, as you can see, we have 2 different probabilities because we are considering both the liquid crystal interaction and the ferromagnetic interaction. Now, we would like to study the microdynamics of our system. So in order to do this, we will follow the Chapman-Kolmogorov equation. And this way we will see that we will find our system of equations in partial differences. We will find a total of 6 equations because of the 6 channels that we are analyzing in our model. And in this equation, you can see that the probability of finding a particle after the interaction in a CI velocity channel will be given by the product of the probability of finding it somewhere else in any other channel before interaction, multiplied by the transition probability of finding it in any other channel and it changing to the CI velocity channel. And here we also define the expected local number of particles given by rho. So here is our equation. Well, we would like to analyze our microdynamics, how our system works near some spatially uniform steady states given by these these steady states. Here there is no net movement of particles. So in order to study how the system works, how the system evolves near these states, we will linearize our microdynamics equation, and we apply a discrete finite Fourier transform in order to transform our equations into these new equations. So as you can see, our new microdynamics equation also tells us the probability of finding a particle in a new channel N, as we can call it, and it depends on some entrances of a Jacobian matrix, which are given by these and the partial derivatives of our transition probabilities. And using this microdynamics equation that I showed you before, we can also define the Boltzmann propagator, this equation number 7. This will be really important for us because using the Boltzmann propagator, we can obtain its eigensystem, and with that we can analyze the solutions near our steady states. So we can see the stability of them. We can analyze the perturbations, and see if they may form some patterns or not. So in this case, we will only focus on the liquid crystal interaction because of time, but there are also really interesting results in ferromagnetic interaction. So for our study, we both did the mathematical analysis and a computational analysis. We performed some simulations with C++, where we consider, well, in this first slide, I consider a constant vision of sigma equals 0. So this means that we are considering a full field of view, a wide field of view. So as you can see, beta is our sensibility. So when beta is low, is small, like 5, we have particles all over the space without any specific pattern or alignation. Then as beta goes up, they start to form these kind of strips, these bands, and where they will interact because there is more interaction between them. So what we are seeing here is that beta is our interaction, and it's better to study systems where beta is up, is bigger, because that way we can see how they are interacting between each other. As you saw before, we first had our system all completely misaligned, and then it started to align into these strips. We can see also this behavior in these graphs. In the upper left graph, we plot sensibility against the liquid crystal parameter. So as you can see, we begin with a system misaligned. So the liquid crystal parameter is 0. Then when sensibility reaches 6, we have a phase transition in which our system stops being misaligned and starts being aligned. This phase transition, we can also observe it in the second graph, where we plot sensibility against variance, and we have this peak in sensibility equals 6. So that means that our system there had a phase transition. We can also plot the sensibility versus the gamma parameter. The gamma parameter basically tells us how our particles are distributed again all over the space. So for example, if it's 0, it means that they are all over the space. But if it's 1, it means that they are concentrated in points. So in this case, we can see that also when sensibility reaches 6, we have this change of gamma because our particles stop being all over the space and start being aligned. So they are aligned in some specific points, but we can see that they start to form these bands. So gamma parameter goes up. Now, if we leave beta parameter constant in 9, and we start to vary our vision, our sigma, we can see that these strips that we saw earlier that form with a full vision start to break into some clusters of particles. And these clusters of particles, they start to go a little bit smaller as sigma goes up. their minimum size reaches when sigma reaches 2. So what this is basically telling us is that as view starts to go down, as you start to see less around you, it's more difficult for you to imitate or follow all your neighbors. So you start only following your closest neighbors, and particles start to just form these little clusters because they can see any bigger than that. They can see any wider than that. This behavior we can also see it here because in these 3 graphs we can see that when we plot vision against the liquid crystal parameter, as our vision goes up, the liquid crystal parameter goes down. So we begin with an aligned system that are the streets in the space. But then as vision goes up, these streets start to break into the clusters, and when vision reaches 2 or even 1, we already have just clusters all over the space. If we plot variance against vision, we can see also that there is some sort of peak, but here in this kind of phase transition, we will have something a little bit different. I will show you what in a minute. If we plot vision against gamma, we can also see that the parameter goes up. So we begin with a system full of streets. The particles are aligned in streets, but as vision goes up, they start to break into these clusters. So gamma parameter goes up because they are more concentrated in specific points. As I told you before, this system has something peculiar, and that is that it has hysteresis. This means that it's not the same to follow one path in one way than backwards. We can see this because in our simulation, when we increase vision, when we increase vision in the same simulation, we can begin with our vision in 0, and our system starts to align in the strips that we saw earlier. But then it's like these strips start to break down into some clusters. So when vision goes to 2, we already have many clusters. And now when we go backwards, it would mean that our clusters will like to group back into those bands that we saw, but it's more difficult for them to do this. So it takes it longer to go back into this configuration that we saw. We can also see this in gamma. We began with a small vision, and as it goes up, we form the clusters, and then the clusters will try to group back into these bands, but it will be more difficult for them, so it will not follow the same path as it went earlier. In this analysis, we also made the mathematical analysis, and we obtained the Boltzmann propagator at q equals 0. Q is the wave vector, the wave number, sorry. And using this, we obtained this eigensystem. So as you can see, we have first the three polar eigenvectors. These are telling us that there will not be some specific direction of movement of the particles, and that perturbations in any direction will not last really longer, because as lambdas, as their intervals are 0, these perturbations will go to 0 really quick, so they will not see really well. Then lambda equals 1 will tell us that there's a mass conservation, sorry. And the last two eigenvectors will tell us that some particles will stop being in some direction and will start to follow just one direction. So that's why we see these streets that we saw, that we presented earlier. And this will depend really on their eigenvalues, that they depend on beta and rho. So if we had a product that was less than 1, these perturbations will go to 0 really quick, and we won't really see them. But if they are bigger than 1, then we'll be able to see these perturbations. At q equals 0, we have spatially homogeneous perturbations in all of our space. And then we plotted some of the eigenvalues for different values of q of the wave number. So as you can see, the eigenvalues they have a peak, have a maximum lambda close to 1.6 to a vector wave number something like 1.6. And this is really interesting for us because, well, first of all, these two, both the graph and the image, were obtained using beta equal 10 and sigma equal 2. So what we can see is that in our maximum lambda, that will be the frequency that will matter the most, that we will see the most. And the wavelength that this perturbation will have will be given by 2p over q. So if we make 2p over 1.6, that is where we have our maximum. We have something sort of 3.9. So this is really good for us because if you see the right image, you can see that our clusters of particles, they have a diameter of 3 or 4. So that is consistent with what we found in our mathematical analysis. So that's all. So here are some of my references. Thank you very much.
Okay, thank you very much for your
Bravo,
presentation. So if there are any questions, now is the time. Okay, Andreas.
So thanks for your talk, which also gave opportunity to learn a little bit of Spanish, at least from the legends. So my question is, I understand your theoretical model, which has liquid crystal interaction and vision, but I'm wondering what is the motivation for this? Is this an abstract model, or can one think of a biological creature which follows this? Because my understanding is that liquid crystal has usually something to do with apolar organisms, and now you couple this apolar agent with some polar vision. I have difficulties to think of any creature following your dynamics.
Yeah.
Maybe.
Sorry. Yeah, we find, well, I'm still doing some research about it, but I found that there is this worm, the C. elegans worm, which follows this kind of behavior. So if you leave them in some space, they start to form these clusters, and they really can see really wide. They don't have a really wide field of view, so they just form these clusters. So this is just some example of a biological creature that follows this interaction.
Okay.
And
Thank
this
you.
yes, and these worms, I think they are really studied because of they don't, you can see through them, so they are really studied for nervous diseases, for example, because you can see all their evolution in their life. So they are really studied in for many things like medical research.
Gracias.
De nada.
Okay, so I think Fernando was first and then Bianca.
Okay.
So my question is the following. I don't know if I follow correctly. I think that you said, I mean, there was two situations. One when the interactions are isotropic, and the other is when you have they are not. And the one you saw, one of the snapshots was the aggregation of clusters. That occurs when the cone is small, right?
You mean this slide here?
No, yeah, the ones that you see these like drops.
The von Mises distribution.
Ah, okay. You mean this one?
No, I was talking about the
Ah,
snapshot.
okay.
Yeah, I mean, that was anyway. And my question is, this, because I got complete, yeah, I see. I mean, you see when you put the cone, right?
Mm-hmm.
There's no longer bands, but drops, right?
Okay,
So, and okay, yeah, that's. I think we have observed something similar. I mean, that the sense that things were getting into this kind of phase separation, a different kind of model, but also the cone. And I was trying to figure out why in this case you also observe these drops. I mean, do you have an intuitive explanation of that? I think there is a coupling with the density, right? I mean, gradient of density here always plays a role, but why? I mean, do you understand this intuitively?
I think I'm not understanding quite well your question. I mean, if you are asking me why these particles start to cluster in these small groups and stop being in these bands, that's what you're.
Yeah, I mean, usually if you try, what you try is nematic interactions. So they will, if they are happy, they will get extended, right?
Okay, okay.
Yeah, but here that you somehow they don't do it. So why they don't do it?
Well, my intuitive explanation is that as vision goes down, I mean, we began with a full vision. You could see all over the place, so it's easier for them to interact with all their neighbors and to make some bigger alignments, some bigger patterns. So they form these strips that we saw with sigma equals 0. But then as sigma goes up and their vision starts to go down, so they can see really a part of them, they can really interact with all their neighbors and they start to imitate or just to follow their closest neighbors. So as they can see really much, they just cluster and they just form these little groups. So that's how I imagine it. Like, it's not that they are not uncomfortable in all the space, but they just can see all over the space. So they just reduce into some little space, some clusters.
Okay.
I think what happens is that they don't like to go, before they like to go back and forth and they go along a line. But when the vision is restricted and they reach like the edge of this thing, of this street, then they can no longer go away. So they just go back. So they get stuck in a small place.
Do these drops have nematic order? Or they are disordered and these particles are basically ended there even though there is no nematic order?
I think we still have to look at that myself, but there is at least local nematic order at the borders. That's why they have like colors.
Okay, that sounds like a bit of MIPS there, right? Could be. All right, thank you.
Okay, so now Bianca and then Thomas Ihle.
And my question is a bit similar. Thank you for your talk. It was really nice. I was wondering how to interpret the simulation snapshot. So you're looking at collective migration, and I'm wondering if I look at this sigma equals 0 on the top left, are they always moving in this stripe back and forth, like Josue said?
Yes.
And in these clusters, are the clusters moving?
No, they are just standing there. You can see, as Josue already said, that in the borders they are a little bit moving, but the cluster itself is just standing back. It doesn't move.
Okay, thank you.
Yeah.
Okay, so Thomas.
Yeah, I was just wondering if I understood the model correctly. It looks like you have that like a exclude volume, so there's a restriction on how many particles can be in a channel or on a site. But in the theory, do you really consider this? Do you take this restriction seriously in the theory, or because I remember vaguely that in these theories there was just factors of 1 minus density which occur due to this restriction. Do you also have that, or is it somehow did it get lost in the mean field approximation?
No, yeah, we consider that both in the theory and in the simulation.
Well, I think what Thomas was asking was about these effects that happen wherein one particle cannot be, or more than one particle cannot be in each channel. So we do not consider that. That's why.
No. Sorry. Okay, I misunderstood. Okay. No, we didn't analyze that case. Just in it. Well, but for simplicity, we only consider one particle in each node. We haven't considered more.
And there's no conflict. I mean, the rules are not like that's two particles want to be in the same channel, but then you have to say no to one of them. Is that in the? I mean, there's certain models where that never happens, but I'm not sure I understand the rules. You know, that I would see that, whether that's possible or not. That can be that you have to make a decision by hand in the simulation. This particle can be in a channel, the other one cannot.
No, so there is no conflict, so we don't have to correct it. So the only thing that would happen was that some configuration is favored where there are more particles like going in like this, you know, instead of going in this direction, they divide into like the closest ones. And with this single particle approximation, we don't consider this in the analysis. However, the analysis is qualitatively the same as if we consider this. It's just not quantitatively, let's say, close. Yeah, that's what happens.
Okay, thank you.
Okay, so I don't know if Andreas has a question, or should we continue with our next speaker?
No.
Okay. Okay.
Thank you.
Well, thank you very much, Marisa.
Thank you.
We will continue with our program then. So now we are going to hear the talk by Dr. Emiliano Pérez Ipiña. So he studied first at Instituto Balseiro in Argentina, and then he got his PhD at Universidad de Buenos Aires. He was working also at Université de Nice in France, and now he's working at Johns Hopkins University. So welcome, and thank you for your talk, Emiliano.
Thank you very much for the introduction, and thank you for the organizer, for you and Andreas to invite me to present my work here. Can you listen to me okay? And can you see the screen?
Yes, no problem.
Okay, great. So today I'm going to talk about some of a new work I'm doing with Brian Kernel that is on collective gradient sensing with limited positional information. So let me start by showing you this movie where we see some lymphocyte cells and their chemical gradient. And this chemical gradient is a shallow gradient. That means that the difference between the lower level concentration and the higher level concentration is small. And what we see from this movie is that there are single cells and there are cells forming these large clusters. And the single cells, if we track them, we can see that they are not moving towards the gradient. They are just performing kind of random walk. While the large clusters or the group of cells, the cluster, they can follow the chemical gradient. So that means that cells get together and they are able to make the collective sensing of the gradient. And that is basically what we want to understand here. So let me begin by remind you how a cell sense a chemical gradient. So basically, the cell has receptors over the surface that are going to bind the chemical molecules, the chemoattractants. And by comparing the occupancy of the receptors at the front and with the back of the cell, they can sense or measure the gradient. So this is an intrinsic stochastic process because the molecules need to reach the receptors, and then we need to have the receptors available to bind the molecules. So this is a stochastic process, and this is going to subject to fluctuations. So that means in the case of in a steep gradient, a cell won't have much problem to make it to sense the difference between the front and the back in the occupancy of the receptors. But when the gradient is shallow, as in the case in our experiment, then the difference between the front and the back might be on the order of the fluctuations, and in that case, the cell is going to fail sensing the gradient. How does a group of cells sense a gradient? So there are many different mechanisms. I'm not here to talk about many of them. I'm just going to present two different models. A first model that is based on cells sensing their local concentration and then sharing this information between each other to make an estimation of a gradient. And then I'm going to present the second model that is a more mechanistic model that is based on some experimental evidence where cells, when they are in contact, they are going to polarize with each other. So let me begin with the first model. So as I said, the idea in this model is that each cell is going to perform an individual measurement of the local concentration. So this is a simpler task than sensing the gradient. Now, it doesn't have to sense the difference between the front and the back of the cell. They just need to sense the local concentration. And then they are going to share this information. But of course, this is again subject to fluctuations, to the reading concentration fluctuations. So instead of having this a perfect measurement of the local concentration of each cell, we are going to have that each cell is going to perform a measurement that is proportional to the concentration at the position of the cell, plus a reading concentration noise that we assume that is a Gaussian noise. And so we are not going to get into the details of what is which is the mechanism that the cluster can perform to estimate the gradient, but we are going to ask a question of what is the best estimator the cluster can make with this information that they have. What is the best estimator that they can do with this local measurement of the concentrations? So for that, we are going to implement the maximum likelihood estimation method. And so in order to solve the problem, we need to write the likelihood distribution. Then from there, we can write the efficient information matrix, and then we can find, actually, we are not going to care about the estimator itself, but the accuracy of this estimator. So what we care about is to find the error of this estimator that is given by the Kremer-Rao bound. So the Kremer-Rao bound is going to give us the lowest error possible that the cluster can make using this information. And so we solve this problem actually for a genetic cluster shape, and also considering that cells can have different errors. But in order to make things simpler and to find simpler equations that are easy to interpret, we are going to assume 2D hexagonal clusters. They are kind of circular clusters. And we are also going to assume a shallow gradient. That means a shallow gradient that the concentration is not going to vary that much between the cells. And in that case, we can assume that the error, the reading concentration errors for all the cells are the same. So if we do that, we find an expression for the gradient sensing error that's given here. So we can see that expression, we have this factor, sorry, this factor H. At this H, it's basically, H bar is basically the ligand receptor variance. So this is the real concentration error of each individual cell. And we have also this prefactor that is a geometrical prefactor that has to do with the shape of the cluster. So now we can use this equation to make some prediction of how the error is going to change or vary with the parameters of the problem. So for example, we can see how the error changed with the number of cells in the cluster. And we can see that increasing the number of cells in the cluster is going to produce a much a smaller error or a better estimation of the gradient. And this scale as n power to the -1. And we can see that if we solve how this term is prefactor scale. So this is going to scale n to the power to the -2. And an easy way to understand this is basically that the precision of this estimation is going to grow with the size of the cluster. So the larger the area of the cluster is, the better estimation that we are going to perform. And this makes sense because the larger the area or the extension of the cluster is, the larger the difference in the concentration between the front and the back, and that is going to lead to a better estimation of the gradient. So then we can use the expression to study how this changes with the gradient steepness or the slope of the gradient. And we can see that our equation for the error that does not depend on the gradient steepness. So here what we are plotting is the relative error, so it's the error over the gradient steepness. And we can see that this decrease with the steepness of the gradient. So basically, the steeper the gradient is, the better estimation of the gradient. And again, this makes sense as the steeper the gradient is, the larger the difference on the concentration between the front and the back, and the better estimation of the gradient. And this is similar to the case of a single cell, where it was easier for the single cell to measure a gradient, a steeper gradient than a shallow gradient. So that was okay so far, but there was an implicit assumption of what we have done before, that we were assuming that cells have knowledge of their position, of the positions within the cluster. So imagine that these two work, cells need to share the measurement of the concentration, but in order this to work, they also need to know where these measurements are coming from. And it's not very realistic to assume that cells within a cluster, they know exactly where they are located. And an example of this is, for example, the case of Bitcoin Drosophila embryo. So we know that cell has limited positional information. So we wanted to include this in our problem. So basically, we were considering so far something that looks like this. All these tables are very well organized, so it is easier to know where the signals are coming from. But probably in a biological system or a cluster of cells, things looks more like here below, like more like a mess. So we included the positional error. So basically now we are assuming that cells need to measure the local concentration, and they also need to estimate their position. So now we are going to assume that there is a positional uncertainty for each estimation that the cells make of their position. And to start, we are going to assume that all these positional uncertainties are the same for all the cells. So again, we can put everything into the maximum likelihood estimation method, and we can find the Cramer-Rao bound and the lowest error with this information. So, and this is the expression that we get. So this expression, it looks very similar to the previous one. So we have the error of the gradient concentration, and we have a new term that is associated to the position uncertainty. So remember that this delta R is the position uncertainty of each cell. And we also see that this prefactor is exactly the same as before. So that means that the dependence with the number of cells is not going to change. So basically what it's telling us is this is going to become more precise with the number with increasing the number of cells in the cluster. But it does change now with the steepness of the gradient. So we can see that before increasing the steepness of the gradient always lead to a better estimation of the gradient. But now in this case, where we have position uncertainty, we can see here in the blue line that it's going to lead to a saturation of the precision that we can measure the gradient, the chemical gradient. And this saturation value is associated to the position uncertainty of the cell. So basically, this is telling us that in the case of having position uncertainties, the position uncertainties are going to limit the gradient sensing of the cluster. And there is a simple way of understanding this, why the position uncertainties produce this difficulty of measuring the gradient. So imagine that we have a cell, and then we have this cell make a small positional error. We displace it a small distance. Then in the case of the shallow gradient, this is not going to lead to much difference in the concentration that we were seeing. But in the case of a steeper gradient, the same displacement, a small displacement, is going to lead to a much larger difference in the concentration. And that is going to produce a much larger error at estimating the chemical gradient. So, so far, again, we are making also maybe a strong assumption, assuming that all the cells have the same position information. Probably in a biological system, this is not going to be true. Probably if we have a signal that is telling cells where they are, this position information might depend on this signal, and also in the position within the cluster. We try to solve that problem, and it is a bit difficult. So we came up with a different idea that is consider two types of cells. So we are going to have cells with large position uncertainty, and we are going to have a second type of cells that has a small position uncertainty. So these are going to be informed cells. And then in order to study the effect of these informed cells over the cluster, we are going to distribute them in different ways within the cluster. So randomly around the center of the cluster and around the edge. And we are going to compare the estimation of the gradient with the case of a cluster with a single type of cells, where the position uncertainty of these cells is equal to the average of the positional errors of the two types cells clusters. And what we see is basically that the case of when we distribute the cells, the informed cells over the edge, we see that we have an increase in the accuracy of the reading of sensing the concentration. And if we distribute the cells around the center, we are going to, instead of having an increase in the accuracy, we are going to have a decrease in the accuracy compared to the single type cell cluster. So what is this telling us is that we need to put our informed cells close to the cluster, close to the edge of the cluster to get the better estimation of the gradient. And this makes sense because those cells at the edge are again the ones that see the larger difference in concentrations. So those are the ones that we want to have the best estimation of the local concentration. Okay, so now we can play a bit similar game, that is, instead of distributing the cells at different positions, we can place the cells, a small cluster of cells, and place this small cluster of cells at different positions within the cluster. And what we see is basically something similar than before. So placing the cells close to the edge will lead to the larger increase in the accuracy. But here what we see is that depending on the direction where we place this small cluster, we are going to see an increase in the accuracy of sensing the steepness of the gradient or a direction in the gradient. So in the case of, if we place the gradient in line parallel to the direction of the gradient, we're going to have an increase in the accuracy of estimating the slope or the steepness of the gradient. But if we place the gradient perpendicular to the direction of the gradient, we are going to see an increase in the accuracy of measuring the direction of the chemical gradient. And actually, if we think about this, what the cluster of cells is probably more interested in measuring the direction of the gradient rather than the slope of the gradient. So in that case, it would be better or optimal for the cluster to have informed cells placed along the perpendicular direction of the chemical gradient. Okay, so now I'm going to talk about the second model. As I said before, this is a mechanistic model that is based on the fact that when cells get in contact, they're going to polarize away each other. And this is called contact inhibition locomotion. And it works basically, as I said, when two cells get close and they get in contact, they're going to polarize away each other. And in the case we have a sheet of cells or a cluster of cells, when we have internal cells that are surrounded by other cells, now the contact inhibition locomotion, as the cell doesn't have any direction where they can polarize, it will result in a cell that cannot polarize. So in a sheet of cells, the interior cells, they don't get polarized, and the only cells that get polarized are the cells that are on the edge. And we can represent that here in this picture, where we see that the cell at the center doesn't get polarized, and only the cells at the edge get polarized, pointing away the cluster. And we can write the polarization in this way as a vector Q that is basically sum over the neighbors directions, and a parameter beta that is the susceptibility of the cell to get polarized by this contact inhibition locomotion. So this is okay, but this is not enough to sense a gradient. So if we want this cluster to be able to sense a gradient, we need to say something else. We need, for example, to ask that the susceptibility to polarize that depends on the local concentration of the chemical gradient. So by combining these two things, we get something that looks more or less like this here on the right. So basically, we have that cells that are up the gradient that sees the larger concentrations, they're going to polarize stronger than cells that are at the back that are going to see a smaller concentration of the chemotract. So basically, this is going to result in a back-and-forth type of dynamics, where the front is pulling stronger than the back, and then the cluster is going to follow the chemical gradient. So, I don't have time to go into the mathematical details of the model, but I'm just going to say that we assume that each cell is an stochastic particle, and we can write the velocity is equal to the polarity and the forces coming from the interaction between the neighbors. We can write that the polarity follows an Ostern-Uhlenbeck process when we have a persistent time, a noise associated to the polarity noise. And we have a term that is associated to this contact inhibition locomotion. And again, in order for this to work, we need to ask that the susceptibility of the cell to get polarized to depend on the chemical concentration. But in this case, we are not going to to ask to depend on the chemical concentration, but we are going to ask that they depend actually on what the cells believe is the local concentration at the position. So this is the measurement of each individual cell performed of the chemical gradient. And we know that this has a noise term associated. So we know that now our polarity equation is going to have also a noise associated to the reading concentration errors. And so we can write the cluster velocity if we sum over the velocities of the individual cells. We are going to see that the internal forces of the cluster are going to cancel each other. So basically, this is going to be just the sum over the polarities. And we can solve the polarity equation, and we can compute the mean values and the covariance. So basically, we can write the mean value for the cluster velocity and the velocity covariance. And of course, this means that the polarity depends on the chemical gradient. So that means that the velocity of the cluster depends on the polarity gradient. So that means that we can associate and we can write this equation where we relate the chemical gradient with the velocity. And then we can propagate errors and find finally the expression of the gradient sensing error for this model. And so we can see from this equation that we have two terms. So the first term has this H bar that is, remember, is the error associated between the concentrations. And we have also an error associated to the polarity noise of the cells. As we want to compare this model to the maximum likelihood model, and given that the maximum likelihood model perform the best estimator or the lowest error that we can make with that information, we want to have something similar in this case. So we are going to assume that the polarity noise is neglected, and we can throw this term away. So two things that we should mention here. So the first thing is that this model does not depend on position information. So we don't need to estimate any position for this model to work. The second thing that is important from this model and different from the maximum likelihood model is the dependence on the number of cells in the cluster. So before, if you remember this, when it was going as n power to the -2, and in this case is n power to the -3.5. And we can understand this because previously the maximum likelihood model were using all the cells on the cluster to make an estimation of the gradient. But in this case, we are only using the cells that are at the edge, that are the only cells that get polarized and sense the gradient. So now we can compare both models. So the first thing that we can compare here is in the case that there is no position uncertainty, then the maximum likelihood model is going to perform better estimation than the tug-of-war model. And that is because the maximum likelihood model used more cells to make the estimation than the tug-of-war model. But as the tug-of-war model does not depend on position information, we are going to see that when we start increasing the position uncertainties, there will be a trade-off value where beyond that position uncertainty, the maximum likelihood estimator is going to perform worse estimation than the tug-of-war. So now we can explore this trade-off value as the number of cells in the gradient and the stiffness of the number of cells on the cluster and the stiffness of the gradient. So we can see that increasing the stiffness of the gradient will lead to that the tug-of-war model make better estimation of the gradient. And we can understand that if we remember what I showed you before, that for steeper gradient, the position uncertainty affects much more the maximum likelihood estimator. And on the other case, if we increase the number of cells, then we are going to see that for large number of cells, the maximum likelihood model is going to perform better estimation of the gradient. And again, this can be understood because the maximum likelihood model uses all the cells on the cluster, while the Tacov model only uses the cells at the edge. So basically, what is this telling us is, depending on the parameters of the problem, a cluster or a group of cells should follow different type of strategies to sense a gradient. And I think I got a bit too extra time, so I'm going to conclude. Thank you. I'm happy to take some questions.
Okay, thank you very much for your talk. It was very nice. I think there was some problem with the slides and at the middle of your presentation, but at the end it was okay. Yeah, it became a bit frozen somehow.
And that happened for everyone?
I don't know, but anyway.
Yeah, I think so.
Oh, I'm really sorry about that.
At the end, we could see all your slides, just that they were a bit out of phase, but it was fine. So
Okay, sorry for that.
no, don't worry. So are there any questions? Okay, so I don't know if Thomas, I think, had his hand raised.
Okay.
Well, if not, Fernando, then.
All right, thank you. It's very nice. I mean, I didn't know this. So I was wondering what is, I couldn't understand, probably was not following carefully what you were saying, or I got lost. I mean, what happens with if there's cells that are measuring those I mean, that wouldn't affect the gradient in itself? And or you assume the gradient is, I mean, those that are sensing there, they do not interfere with the amount of whatever is around.
Yeah, exactly. We are not assuming, we are probably in a limit where the chemoattractant is so abundant that binding to the cells doesn't affect the concentration. But there are actually some people that have been working on basically that the case that a cell itself degrades the gradient by binding to the receptors. So yes, that could happen, but we are not on that limit.
But in that level where you have an abundant amount of whatever chemoattractant, so still you have this kind, I mean, this is not a function, the level of noise that you have in estimating as well related to the amount of molecules that you can measure and the frequency at which you measure and so on. I mean, the more you have, I guess that you get, I mean, well, the information comes to you. That's obvious. If not, it's...
So there are many, yeah, so this ligand, so binding the chemoattractant molecules to the receptors, if the concentration of the chemoattractant is very high, that would lead to a saturation of the receptor over the surface, and then the cell is not going to be able to sense very accurately the concentration of the chemical rate, the local concentration. So there is an optimal concentration where this error is going to be the smallest possible, and that is when the dissociation constant is equal to the concentration of the chemoattractant. So yeah, that would affect. So we are basically assuming a situation where the concentration is basically close to the constant dissociation, so we don't have any of this effect of saturation of the receptors.
Okay, thank you.
You're welcome.
So is there any evidence that these two different strategies could be turned on or off in the kind of cells that you're looking at?
So the evidence, they are actually pointing to the Tacov model. So basically on the same experiment, that I showed at the beginning in that movie, then they performed some experiment to see what was happening with the polarizations over the cluster. And what they actually saw is that only the cells at the edge get polarized. And that makes sense because these clusters are on the order of the 10 cells to the 100 cells. And those are more or less close to what we found, that the tag of war should be optimal than measuring the maximum likelihood. So the maximum likelihood is kind of a theoretical limit. But in that case, you should also consider that you need to estimate your concentration, you need to estimate your position, but also then you need to communicate all this information. So there should be also some source of noises associated to the communication that we are not considering here.
Yes, of course. Are there any other questions? Okay. Well, if there are no more questions, then we will take a break until, and we return in half an hour for the second part of our speakers. So thank you very much. I will pause the recording now so that you can speak freely if you want. And I will continue with the recording once we come back. Okay. So it's recording now.
Good.
Okay. So welcome everybody to the second part of our workshop on active matter. Many people, or probably most of the people, are complaining about COVID, and I would substantially agree that COVID brings lots of big problems, but there's also a few benefits, I might call them. And one benefit is this video conferencing. So I think this type of workshop has been triggered by COVID, and it serves a lot of purposes. So we do something for sure climate friendly. None of us has to board a plane and go for long distances. And we have now participants today from Mexico, from United States, France, Germany. Maybe I forgot some country, which is quite nice.
Austria.
Austria. Sorry, Oleksandr. Fortunately, you are not Austrian. Otherwise, it would already create a political trouble if a German doesn't recognize that there's an Austrian participant. Yeah, sorry. Yeah, so we are lots of different people sitting together. And I don't want to waste more time and welcome Oleksandr from University of Vienna. He started his career at the University of Odessa in Ukraine, finished his PhD in Nice, France, and after other postdoc positions, he's now having a postdoc position in the Physical Institute at University of Innsbruck. And we are very much looking forward to your presentation on circle swimmers, and you will tell us what this means. Thank you.
Okay, thank you very much for the introduction. Well, just tell me if my internet connection is fine, because maybe not that stable. Okay, so thank you very much, organizers, Andreas and Jose, for this opportunity to present the work that we have been doing with Thomas, well, quite recently. So this story I'm going to talk about now is in principle a very new story, very recent story. And well, this is the first time I present it anywhere, so maybe some parts are a bit raw, but yes, I will be glad to present them and to discuss them and to get some feedback. So yeah, so we will talk about gravitaxis of circle swimmers, microswimmers, active particles, and some interesting phenomena that are observed in it. So I'm starting with a bit of this slide with different works on gravitaxis that appeared recently in experiments, in simulations, and different theoretical studies. So this is just a few examples. Of course, there are many more. So when the question arises, how the behavior of active particles will change if the active particles are subject to gravity. Yes, and for example, here, yes, there's an example of microswimmers moving up the wall under influence of gravity. There are different works that discuss in experiments and in simulations the sedimentation profiles of such active particles. But well, not so many work focus on temporal evolution of quantities such as mean square displacement or so on. So we looked at one particular experimental and theoretical study, one of published in 2014 by a group of Artmut Leuven theoretically and Clemens Bechinger experimentally. So when they consider gravitaxis of a symmetric self-propelled colloidal particle. And so we looked at this interesting experiments and well theory. So here in this experiment, they consider a particle, L-shaped particle, which is what is interesting. It can move in circles. So active particle, which is also has some rotational motion. And then they subject it to an external field. So another talk about external fields in active matter. So it's subject to gravity, and it shows under different propulsion speed, yes, because they shine light on this particle and it changes its Peclet number, so it can move faster, and also its rotational diffusion changes under this influence of light. Also, they can change this strength of this force, yes, so this gravity force by this change in this angle. And they observe interesting behavior. So sometimes when the light is low, yes, when it just moves down, but then increasing light intensity, the particle move in a circle, this like spiral trajectories, and can move in straight trajectories upwards, for example. So this peculiar behavior, yes, so they characterize it with, as I said, this Peclet number, so intensity of swimming, let's say, and alpha here, it corresponds to gravity. Yes, so the gravity force, because they can incline, and then they have a plethora of trajectories, and again some like very straight trajectories and some spiral, say, trajectories depending on a parameter space. They have introduced an interesting theoretical model, quite complicated model with some hydrodynamic. Well, we don't go into details of this model, but okay. So the position of particle in time develops according to some equation, and the direction of it develops according to another equation, where some rotational dynamics is included and encoded in all these complicated symbols, and some gravity force and gravity torque are applied, and some random noise. So with this theoretical model, they did something interesting. They said, okay, if we neglect noise, what is the direction of motion in long time limit? Yes, as we saw, the trajectories have very defined characteristic direction of motion. And this is the comparison of the theoretical result from this model and experimental points in their experiments. So we decided that this model is interesting, the behavior is interesting, and we decided to study it in more detail. And first of all, we have rewritten their quite complicated way of writing this model. We decided to simplify, so we applied some simplified notations. And after using these some simplified notations, we have written quite simple equations of motion. So we decided to write it in a simple way and study the properties of such a model. And essentially, what do we have here? Here we have the position of our active Brownian circle particle, circle swimmer. It changes in time with constant velocity in a direction theta. Here we even drop off the gravity force, yes, that would somehow act and change, say, y coordinate of our particle. So we consider very, very simple case. So where only our coordinate is only changed due to self-propulsion, and the direction of motion is changed due to angular drift. like circle swimmer model, yes, and then we have usual Gaussian noise term. And what we introduce here is this minus gamma sine theta term, which tells us this external torque caused by gravity that orients our particle in the space. So here our external field is modeled using this simple term. So we write the equation of motion in such a way, and then we simulate everything with Langevin dynamics. What we find interesting that, of course, when you change the gamma, this prefactor, strength of the field, let's call it, when you change it, the trajectories change. Yes, so from some kind of spiral trajectories, they get straightened and they change the average the characteristic direction of motion, let's call it. But also, if we fix gamma and change only rotational diffusion, the direction of motion, characteristic direction of motion is also changed. So here one cannot simply drop out the dependence of rotational diffusivity on, so the dependence of the direction of motion on this rotational diffusivity. The direction of motion is quite complicated. It has complicated dependence on both, on all, in principle, parameters, on omega, on gamma, and on rotational diffusion. So on internal drift, on this external field, and on this rotational diffusion. And then, okay, we saw that this is quite complicated model, and we, okay, decided what we could do, how to study it in more detail, and even to look at temporal evolution of different statistical quantities that can describe it. So this is briefly that we also can write solutions without noise in terms of our model, and we will use it a bit later. This is just quick. And so what do we do? How we get exact time dependent, exact, because up to some numerical, of course, integration, let's say, how to get some exact time dependent moments. So we use the next expansion of intermediate scattering function as so in this, yes, so this k wave vector. So if we get this expansion, then coefficients in this expansion would give us average displacement, average mean, so mean square displacement, and in principle we can get any terms of higher order. But here we will, in the following, we consider average displacement and mean square displacement. So how we get this intermediate scattering function? To get so we can get this intermediate scattering function from Fourier transformation of probability distribution function, and for probability distribution function itself, we can write a Fokker-Planck equation. Yes, from equations of motion, we can write it, and if we solve it, or we get some expression for this kind of expansion, then we can get what we want. So this temporal evolution of averages. So what is the strategy? So here is we employ a bit complicated strategy. Now we are thinking about how maybe to present it, but I just tell as it is now. So we introduce some basis, and then we employ Dirac notation. And so by employing it, we, well, one can show that in this Dirac notation, we can get such a time evolution operator in some representation, in some theta can be rewritten in this operator form, where we then apply perturbation theory. We call this part unperturbed operator because it doesn't have k, and then we call it perturbation operator this part because it does have k. So this small k, this that we will then use as an expansion to get our what we want. Yeah, so here you call it perturbation operator, and this perturbation operator, so it has this kx and ky, so it contains, so as we write it, contains both x and y components of all this mean that we will, quantities that we will look further. So to get it as we have it, we can write the solution. So one can show this part, yes, so that intermediate scattering function is such an element of our distribution function. Yes, so or this operator. And then, okay, so a bit of this, write the second order perturbation, and we can integrate it. And here you can see that after integration, we get an expansion, and this expansion is exactly the form that we wanted for intermediate scattering function. Okay, so what do I mean? That, okay, the first term will be the first order in K, and this will give us the mean displacement, and the other two terms are of the second order in K, and they give us mean square displacement. This term, as it is proportional to t squared, gives us a ballistic part or directed part of motion, and this part gives us well, mean square displacement. Let's say the part is proportional to time and some exponent. So here, well, there are some details on how exactly we compute all these elements. So we compute eigenvectors and eigenvalues for this operator, and that allows us to compute these well, terms. Okay, this we probably skip. And okay, so this is the result we get. So once we perform our once we perform our numerical scheme, we can get that this element is average cosine and well average sine, and we can plot how the average cosine and average sine depend on the ratio of gamma, so this external driving, to omega, to angular drift of the internal property of our particle. We see, interestingly, yes, so that for cosine, there is an interesting dependence on gamma, that at gamma to omega 1, there is a transition, yes, and it depends on noise. Interesting also for the sine theta, average sine theta, that it has something that resembles a resonance, yes, that it peaks around 1 when external drive and internal drive coincide. Also, this can be represented in different ways. So if we employ characteristic angle, as we discussed before, so the kind of average direction of motion, that we can see that up to ratio gamma to omega 1, it doesn't depend on gamma, and then it quickly changes, and then its dependence becomes very pronounced. Or also we can compute how much the motion is, say, ballistic or directed, and we see that for low gamma to omega, the motion is dominated, say, by diffusion, diffusive behavior, but as gamma to omega increases past 1, the particle just moves in a directed way, as in ballistic, let's call it, way. So these are the first two results, and here we can already compare this our characteristic angle with the angle from experiments and from simply theory without noise that we looked before. So here is again the picture with experimental points and the theory without noise. Here is how this exactly, so orange curve shows us how it improves when the noise is taken into account. So how asymptotic behavior, for example, improves. And okay, the green curve is exactly this blue curve on the left. So in this experimental regime and these parameters, probably the difference is not that big, but we expect that in other experimental parameter space, probably as we explore it in some region of parameter space, the difference could be more important and could be measurable in experiment. But this is about average direction and average motion. And then the next is what happens to more interesting things like diffusivity. Yes? So we define diffusivity as the derivative of variance, which we can compute, and then we can get the exact expression in terms of these elements for diffusivity from our theory. Also, we can get this expression from simulations. So the points on this plot are numerical simulations, and these lines are computed with this theoretical approach. And we see that when gamma to omega ratio approaches 1, the diffusivity, so relative diffusivity to the diffusivity without gamma, peaks, and we see this huge amplification of diffusivity, and exactly in the pattern as one would expect in a resonance phenomenon. So for high noise, the values, so rotational diffusion values, we see flattened curves, and for low rotational diffusion, we see curves that peak in this way. So yes, we see that when the external driving and internal driving coincide, we get a huge amplification of diffusivity that we could even call resonance. And what is about the variance itself? So the variance itself also can be computed, yes, from our theory. And we see that at low driving, we still observe some oscillations in the variance, which get damped as the driving is increased. And then for high driving, we see that the diffusivity is, well, by itself decreased, and there are no more oscillations in the trajectory, yes, in this variance. And a bit of how we can kind of rationalize it, we can, so for gamma zero, it's known these properties of eigenvalues or first eigenvalue. Yes, so why is important? Because here, yes, this eigenvalue in exponent, then it tells us about oscillations. So it shows that, okay, the damping of oscillation grows with gamma to omega increasing, and then the and so this oscillation frequency quickly goes down with gamma to omega increasing. So this is how exactly these oscillations decay. And so thank you. So this is the conclusion now. So we shown the resonance of diffusivity in Gravitaxis for these chiral active particles. We developed an analytical theory which in principle predicts temporal behavior of moments in principle to any order. We can construct it for chiral active particle displacement in Gravitaxis, and we compare the results of our theory with numerical simulations to a certain degree. And in future, we want to write down a full intermediate scattering function, study this system, but in heterogeneous environment, and then probably some implications for collective motion of active particles could be found as well using our single particle model. But okay, this is something for future. Thank you very much for your attention.
Thanks a lot, Oleksandr, for your interesting talk. You definitely get a new contribution in Guinness Book for the fastest talk within 20 minutes. I assure this. But are there questions? So we have raised hands by Thomas. Hello, Thomas.
Oh, yeah, thank you for a very nice talk. I was wondering, do you have an intuitive understanding why you have this resonance in this derotational? Is there some simple picture one can imagine?
Well, this is what we are working on now, actually. So we found it, yes. So we found that, so this is spatial diffusion, yes. So somehow when this gamma to omega is increased, the spatial diffusion first grows quickly up and then drops very quickly down. And in principle, I think, yeah. So why it drops quickly down? Yes, because it gets very much oriented by this external torque, and then it just follows one direction. But why it grows up? And yes, so this is what we are now working on, discussing and thinking how to present it, actually. Yeah. So.
Yeah, thanks.
Jose?
Okay, thanks. Yeah, so you showed a plot where you looked at the average velocity, right? That it was going from 0 to...
Yes.
Yeah, exactly.
This one, I guess, yes.
Yeah. And then you were saying that you could see here that you transitioned from something that was diffusive to something that was more ballistic, right?
Kind of, yes, kind of.
So I was wondering, because your particles rotate also, right? So
yes.
I was wondering if there was some regime where the rotation of the particles was so strong that it was actually sub-diffusive and not really diffusive, you know, and then, so I was wondering if there was this kind of transition from sub-diffusive, diffusive, and then super diffusive.
Well, so let's look at, so variance. Yes, we don't look at mean square displacement because, okay, we subtract this average part. Yes, it's proportional to t squared. We look at variance. And in variance, then I think it pretty well follows this relation. So here is this kind of diffusion, yes, and proportional to time. And then there is this thing that corresponds to oscillations and their damping. So in principle, in model as it is, we don't see subdiffusion. Yes, I would say it like that. Like, well, can this be, I don't know, interpreted? No, probably not. Probably not. Yes, also, yes, so when this gamma becomes too strong, it doesn't do any circles anymore. Yes, it just goes in one direction without. And then, okay, there are fluctuations, but there are no more circles. And the circles are only for this low gamma regime. So we're here. Yes. Yeah. So then they quickly turn into like straight lines and directed motion.
Yeah, true. Okay, thank you.
Yeah.
There is a question from Emiliano, please.
Yes.
Yeah, so I think I got lost at the beginning because you started with some particles with L shape, but I didn't get how you get the shape with your model, or if that matters.
No, so here it doesn't matter. Here what matters for a model that these L-shaped particles, they can go in circles and they're active particles. So that they have this self-propulsion and they have, because of L shape, they move in circles. And then in this paper, in this Nature Communication paper, it was shown how you can write for L-shaped particles such a model. So with all these coefficients encoding L shape somewhere inside them. And then we do kind of even next step, and then we encode everything in these simple coefficients. So somewhere here, this is hidden, but we kind of don't exploit it, yes, in our studies. Yeah. We just, it's somewhere in omega, yes, but.
I see. Okay, thank you.
Yes, are there other questions also from the maybe junior participants of our workshop? Don't be shy. This is a possibility to ask questions now.
If not, I'm allowed.
Yes, Fernando, please.
Okay, thank you. So I was a bit, I saw that Emiliano was going to ask that. Because we have been working on chiral active particles used to describe Escherichia coli on a surface, and that these guys do the stops, and then there was with Salmonella. And then we also observed basically the existence in the paper on Escherichia coli, that was the stops. Also, you have a resonance if you want. Something that peaks at a given value at maximize the diffusivity, and that we also observe in the other. In a recent paper from this year.
But what do you have on x-axis? What do you have on x-axis for this? What do you change?
Yeah, if I share screen, I show you. But I cannot, right?
Okay, well, I don't know.
Yeah, then I show you when I have to talk.
Yes, we just okay.
But this in one of the axes that we put was I will read what I'm seeing is in one was the transition on that model complicated with the stops. Okay, so we can perhaps forget about that. In the other one was I'm trying to get where I put this thing is the where is in that axis? I think it's omega. Yeah, it's omega, and basically you have it
gamma over
omega or d theta. Sorry, d theta you have, and basically that's also going to have a maximum in there, not that sharp, at least in the regular expression, because what we observe, what we obtain is basically the same expression that you put. That where you put the reference to Franos.
No, but there are many.
Yes,
works. Yes.
Yes. So you have that expression, and that expression also has a peak, right?
Yes, if you plot versus diffusivity.
Yeah, or you put it if you plot that stuff. This d naught, if you plot it as function of d rod, for example.
Yes.
Of if. And so why here you need, or what is so important having the gamma?
Well, this is an external field, and this is when you change an external field, you get the resonance. Yes, so you have one frequency, and when one frequency meets your internal frequency, you have an amplification of diffusivity. Yes, so this is
But you
and
don't have
real
something
resonance.
similar already in this expression where you have d rho that may be comparable with omega. Anyway, so I think.
Well, but it's different influence.
Yes,
no,
yes.
that's
So
noise,
basically,
and this is external field. Yes, but
yes, I'm trying to understand what qualitatively is different here. I mean, you are comparing with that, and so there is a new element clearly, and I'm trying to understand how that brings, what is the new physics that is bringing that, which I'm missing. I'm asking you if you can explain me. What is that? I mean, the other also has a peak and so on. So I get a bit lost on what is what is doing that is qualitatively different that field, which I would have assumed that brings something fundamentally new, and perhaps I'm missing most probably the point.
I write down. Yeah. So, well, our opinion, yes, that the external drive can cause such a thing. Yeah, in principle, one could say, yes, there is some external periodic force, and then you could expect resonance, yes, of something. But I don't know if there is a resonance of diffusivity. Also, this could be probably rationalized as an example of stochastic resonance, but okay, we don't touch this in this talk, and this has to be some work done also on that, yes. But yeah, so for the moment, I see only like, well, this is why it's raw material, yes, and that's why we are still working on how to present it, because we also, yes, we're also working and thinking about this question, what exactly is some new physics behind it, some more deep, yes, understanding of it. So for this effect that we found in simulations, yes, we found in our this analytical, same analytical theory, but yes, so this is something we are still thinking on, and especially how to present it. Yes, this is what we are working on now.
Okay.
Okay, thanks again, Oleksandr, for your presentation and discussion. And we move to
everybody.
We move to the very last session of our workshop. So far, we have already listened to very interesting applications of active matter, both in theory, but also in applications, biological applications. And it's a great pleasure now to have Fernando speaking, because I'm probably not wrong if I say that he is one of the key movers of the active matter field. He has both contributed to extending the theory, but also has always been interested to extend potential applications of this active matter. Thomas was citing Vshape model from 1995, which has several thousand references already, but it's mostly in theory. It's not so easy actually to find applications of the standard model and extensions, and Fernando has come up with some ideas in this direction. So his origin, his scientific origin was in Buenos Aires, Argentina. For PhD, he came to Germany, Dresden, and Berlin, moved on to different places in France and Germany, and today he is a full professor at Cergy University in Paris. I'm not sure if I pronounce Cergy correctly. You can tell us better, and we are looking forward to your presentation, Fernando.
Okay, thank you very much for that very nice introduction. So you see my slides?
Yes.
All right, great. So I will ask you to, I mean, if that's okay with the, thank you, the organizers, for this very nice invitation. And if that's fine, I would encourage you with the organizer to interrupt me if there is something that is unclear. Okay, so I'm going to talk about intermittent collective motion, and then before starting with that, I want to make a kind of summary of many of the aspects that I want to highlight of collective motion. As you see here, I put a canonical view. So it intends to be that, a canonical view, but also to be a bit provocative I mean, because there are several aspects that that we are going to somehow call into question. So if you think of collective motion, most people, and that also goes to the Vshape model, will understand as collective motion a group of particles that go in the same direction. Something that will be key for us during the talk is that one assumption is that these particles or the collective motion is a continuous and interactive process, in the sense that particles constantly move and they constantly try to align to neighbors. So in that sense, that there is no interruption of that process. And all theories and everything has been conceived and analyzed and experimented, even assuming that we are in a phase where everybody is moving and is moving collectively. At least may have different phases, but clearly, I mean, the process we see is a continuous process, in the sense that you are not going to switch off that collective motion and put the particles at rest, or modifying everything that happens there by doing some sort of resetting. So it's a continuous process in which something happens, and that happens is velocity alignment. That is what was proposed by Vshape, that is pretty much inspired in the XY model. So the idea there is that each particle is going to adopt, is going to look at the velocity of the particles in a radius of interaction, and it's going to compute the average velocity in there, and it's going to adopt as its own velocity the average velocity in that neighborhood. So the particle is going to do this, as I'm showing you here in this slide. So for us, another aspect to consider is that this typically, I mean, that depends which context you are looking at, but as a democratic process, or I mean, it at least is cited even in social physics and social applications as a model in which consensus emerge. So particles reach consensus, in this case, on the direction of travel. And what is very important for us is that the mechanism that leads to consensus is also what allows the particles to perform information pooling. In fact, here, both things, by how the model has been constructed, information pooling occurs in a kind of natural way. Everybody has to compromise and they go to the average direction. And that means that if several of these agents of these particles, active particles, will have a preference in the direction of motion, for instance, they know where a target is located of interest for these particles, and they have, I mean, some knowledge on the location of the target, but they are prone to error, so they don't know exactly. They can do what this information pooling, that is, they can bring together all that information, and you can show by that in the Vshape model that is going to happen, that they can localize that target with higher accuracy of what they do it if they do it on their own. I mean, if you think of one individual particle, it's not going to do as well as they would do as a collective. Okay, that means that information pooling is something that occurs also in the Vshape model, and this information pooling is what was discussed by Cousin, and that became was an important contribution in the area of animal behavior. Okay, now what happens when you see a group of sheep? If you see a group of sheep, then what you are going to see, this is a group of 4 in an arena that, if I remember correctly, is 50 meters by 50 meters. And there is another one arena that is 80 meters by 80 meters. And what you can see is that these guys, what they do is they move together from some period of time, but they also perform, they stop. Here they are not moving, now they will start moving again. And if we wait a second, you will see them moving. Okay, so as you saw, the collective motion here occurs in bursts. So they are, if I go again, you see them like not doing much, and at some point all of them will start moving, as you can see here, and then again. So another observation is that when they move forming a line. Okay, so the first thing is here then that what we are observing, at least in sheep, and we think this is something quite general, is that typically animals and in many biological systems that is going to be true, they are not constantly in a collective motion phase, but that collective motion phase is going to start at some point and it's going to stop at some point because animals also have other needs. And then for the case of the experiment, we are going to say that the collective motion phase is when all of them are moving together, and we are going to recognize some phases where the animals don't move or move very slowly. And now the key, I mean, conceptually, what we are going to do is we are going to think that collective motion in itself should not be considered like just one event, one of these straight lines that I'm showing you here. This CMP stands for collective motion phase. It's not just consistent of one collective motion phase, but consists of the many collective motion phases that you can see here. That means the goal, I mean, if you think that that collective motion occurs because there is a biological intention or purpose of that collective motion, the intention is not to be fulfilled that in one collective motion phase, but on many. And that is going to bring us to what I'm going to discuss next. But that you can see here also is that each of these collective motion phases, because as I show you in the experiment, they form a line, they form a file. So you have the individuals, the colors here indicate different individuals, and these individuals are changing from one collective motion to the next. For example, here, the one at the front is the black one, which is the last one in this collective motion phase. So the questions that I'm going to be, I mean, by looking at the experiments, what we will be doing is we will try first, not the kind of standard questions that we ask when we think of the Vshape model, but rather questions that probably we should have asked at the very beginning. I mean, when we need to conceive a flocking model or a model that does produce some collective effect, and in particular collective motion. So one of the questions that is central for us is to understand how in these experiments information flow, and in particular what we want to know is how is the interaction network, that is what is the influence of each individual in the group with others individuals that are in the group. Who is affecting whom? That's the question. So what we want to know about that, what I'm going to call as interaction network, is whether that interaction network is symmetric or whether that interaction network is asymmetric. And we want to know as well, I mean, related to that is whether the interactions are reciprocal. So the other question that we want to ask is, while the group is on the move, while everybody's moving, what is the information that they are sharing? Or if you want, I mean, if another way of saying it is that we want to know whether the navigation during that collective motion phase, while the collective is on the move, is by exchanging velocity information, or is by exchanging positional information, or is by exchanging both of them. Okay, so the other question is, as you saw, there is one individual at the front, and I'm going to justify later that that individual at the front, in fact, is actually genuinely a leader, a temporal leader, a leader of that collective motion phase. And we'll try to see how often individuals are lead and what's the probability of becoming a leader, a temporal leader. So now let me show you, this is experimental data. This is a group of 4 again. Now you are going to see that the group is going to be led by individual in red. If you wait for a while, I think, yeah, now it's the purple individual. And so one main question here is, if you are looking at that, if there is a temporal leader, and as I'm going to show you later, the network is hierarchical, if in that in this situation, how can individuals exchange information, and how can they do information pooling? And basically, another question related to that is, what is the advantage, if any, of having a temporal leader? Okay, So I'm going to start by giving you the answer and the conclusion, and then see how far I go with the explanations and so on. So, but basically the take-home message here would be that by performing intermittent collective motion, SHIP take advantage of both hierarchical and democratic strategies. And in which sense and which kind of advantages I'm talking about? For example, one is the one advantage that you can associate to hierarchical structures or strategies is that you can ensure group cohesion. And on the other hand, is that you can also ensure, or you can show that there is an efficient guidance in a complex environment. For example, I'm talking about this. If someone knows, how to navigate this maze, and this is acting as the temporal leader, will manage to guide the entire group to the target. If you replace that for something like it, and for doing that, you also need the structure, the interaction network to be hierarchical, as well as to exchange positional information and not velocity information. If you do exchange velocity information, they won't manage to do what you have just seen. And then what we are going to see, and what another advantage of performing intermittent collective motion and using temporal leader is that this is still possible to perform pooling of information. And there is also possible by that strategy to make use of private information that individuals may have. And that private information might be of a different type. That means individuals may not all of them want to go to the same place, but they may want to visit different places. Suppose one individual may know where water is located, and some other may know where grass can be found, and then they can make use of that. And in order to do that, if you use something where constantly they are debating what to do, basically what they won't manage to do it. So this strategy, however, will allow them to make use of private information. So now comes whether this kind of things I'm talking to you about SHIP is only about SHIP or a small group of SHIPs and phi formation or lines, lanes as this one of SHIP you can see in that can be very large. And then you have many animals where the structure is hierarchical and they form files and so on. So these things that we are going to discuss more probably can be applied to several different type of biological systems. So now, I don't know, I'm a bit lost on with the time. So
yeah, 5 minutes left, Fernando.
Oh my God. Okay. So okay. So there are a few things. So now let's forget a second about what is happening in space. So I want first to focus on the question to move or not to move, right? And in order to do that, you can look at one individual. And if you look at one individual, what you can see is how this, you can look at the statistics for how long they move. This is speed as function of time. And as you can see, this is what happens for the individual number one. And then you see that it's not moving for a long period of time, but at some point is moving. And then you can ask yourself, what is the statistics of these periods where the individual is moving and the statistics of periods where the individual is not moving. And this you can do because the distribution in speed is clearly bimodal. So it's very easy to go from this kind of signal to a binary signal and to do this kind of statistics. So now what happens, this is the distribution, one of these individuals, one group member will be moving, and this is the distribution of time is not moving. And if you think that you can explain this with two states, in fact, you cannot, because in the distribution of stop times, you will expect as well, if you have two states, you expect an exponential distribution, which is not. The solution is to assume that you have three states. And what are these three states are the ones I'm showing you here. That is, SHIP could be not moving with the head down, which you can assume that is grazing, or with the head up, or it could be running. And Okay, with that, you can do, with this definition, you can go to the experiments and compute for how long is in each of these states. But now what happens is that what I show you was what happens with the first, an individual we label 1. But then if you look at the behavior of all the other individuals, this is the speed as function of time again, you see that they are highly synchronized. So how can you understand that level of synchronization? And in order to understand that, you have to assume that basically these guys are this, I mean, this is what we saw for one individual, but if they show this kind of synchronization, that means that transition rate depends on the behavioral state of the neighbors as well. So basically, if I'm not moving and someone start moving, I may be tempted to move, and I'm going to decide whether I move or not, or I stop, taking into account what the others are doing. Okay, so then you can do experiments with that. This is with a trained sheep. You have a sheep with a vibrating collar. You can call this guy. The guy is going to go to that panel, and then you can check the experiments. Basically, you have the individuals, that is the trained individual, this one, you make it move, that is going to move some individuals around, and you ask yourself what happens with one individual that is behind, and basically you want to know how that transition rate of that individual is going to be modulated for the one that are running and the one that are not moving. Okay, this is an experiment that I'm going to skip. Oh my God, I want to show you the XM Grace. Okay, and by doing that, basically you can obtain what happens, how are these transition rates. And once you have all that, what you can do is basically put a model and compare these are the experiments, and then you will see what happens in the model, and you get a behavior that is quite comparable. Okay, so now that we know how we can basically transition from one state to the other, now one piece in the puzzle is to know that the first individual that start moving typically is the one that was acting as a leader in what you saw before. The second individual, I mean, the first individual to follow this one that made the first transition is the one that was second in the file, and so on. So now, though I mentioned this for sheep, clearly this what we are talking about is imitation, and imitation also you can find in humans, that they tend to imitate what others are doing. This is with kids, but that's also true for adults and so on. So these kind of ideas you can apply most probably as well to human behavior. Okay, so now I'm going to rush with the questions that most probably I'm not going to talk much about. That is what happened now that we understood how is the selection of a leader, and who is first and who is second in those files. We can ask the following questions that we formulated before is, how does information flow while the group is on the move? What information is shared among the individuals on the move, and which individuals are temporal leaders? And this is basically what I showed you before. That was one experiment, so we can skip it. What I want you to remember is that they tend to form these files, and then by basically looking at the correlation in velocity correlation between these individuals, you can identify who is affecting whom, and basically you can reconstruct the interaction network in there. And basically we found that is this one, the one that explains the experiment the best. And also you can try to put different type of interaction. You can ask yourself by playing with different type of equation of motion, whether they will do these files, and they will navigate by using the position of the neighbor or the velocity of the neighbor. And the conclusion is that at least in the experiment with sheep, they will do it just using the position of the neighbors. And the main reason, if you have velocity, basically they will not form these files, these lines, but if they have positional information, they easily do it. And then we made the statistics on who acts as a leader, and we found that everybody has the same probability of acting as a leader. And then we basically were playing what they can do by, once we have basically deciphered the kind of interactions and role they use, And basically what we realize is that, I mean, if they, what I showed you at the beginning, if they exchange velocity information, typically they cannot, for example, even if someone knows how to go from the entrance to the exit of a maze, cannot guide the group, but with the rules, I'm telling you, they will able to do it without much of a problem. And then they can do information pooling, because each time that someone acts as a leader will move the group in the direction where thinks that the target is located. And then if someone else is going to guide, the group will also do it in the direction it's thinking the target is. So instead of, as in the Vshape model, performing spatial average, here that will become a temporal average over the different opinions. And then you can also perform information pooling. This is connected to something that is called the Galton problem, and connected to wisdom of the crowd, if you are familiar with that. And then this one shows you how they can basically explore if they have different type of information, different targets. And in here is how you can make use of private information. And there are different strategies that you can play with. Like, for example, if everybody is trying to impose their opinion, or they will basically accept that there is, for a period of time, a leader. And if you do that, you can see that is the one that outperform all the other strategies. Okay, and this is basically the summary of what I just told you. So with that, oh my God, okay, this is what I mentioned before. So basically the advantages, and I finished. Thank you.
Thanks, Fernando. Great. Also that you left us some time for discussion, and that you drew a connection to next Sunday in Germany, where we will have national election, and this will be the last day. It will initiate the last days of Angela Merkel. But this is only a side comment. I have to think deeper if I can learn from your talk something for the outcome of the election. Other questions?
I think Thomas has a question.
Thomas.
Yeah, at some point you showed this transition between collective motion, where they all move with a goal, and then they just more or less hang around at some point. And you had this process with two states, and that was the two distribution of time. So I was wondering, the distribution of these times, do they have a long tail? I mean, did you ever encounter an example where let's say the mean time?
I mean, in the experiments, we don't see that. It's true that something that one could do is assume that those periods maybe have fat tails. I mean, the distribution. And this is not what we are observing from the experiments. No, they seem to have, I mean, obviously we have a finite number of experiments and so on, but from the experiments we have is not evident that none of these periods, the non-moving ones or the moving ones, have I mean, maybe power law distributed. I guess that is what you are suspecting. So yes, though perhaps we don't have enough statistics, but there is no indication of that.
But in principle, you can model all types of distributions if you just include intermediate steps. Not just the three.
I mean, I mean, if as you increase the number of steps, you can increase the complexity, let's say, of the distributions. I mean, that's one of the key observation is that, in fact, most probably they have more than one internal state. That was one part of that, because if you have just one internal state, you cannot do it. Just I move or I don't move, that you cannot explain. So you need more, and that is important if you are interested in accounting for the shape of these distributions. I mean, but then if you have three, also you have a limited number of possible options if you assume the transition between the states that you are adding is always exponentially distributed, right? So it's not true that if you have five state, I can fit whatever I want, or so that depends on the topology of that network and I mean of the Markov chain and so on, but there is a limited set of options.
Yeah, thanks.
Emiliano, please.
Yeah, so I was wondering, and this is just curiosity. So do you have any evidence that, for example, in the case of the maze, the ship that knows how to solve the maze is going to be always the leader?
No, I don't know. I mean, we don't know that. In fact, the main intention of this study, I mean, yes, we try to understand what happens in ship, but in fact, the intention was to rather go and say, well, most probably we have been thinking for 25 years on the Vshape model, and there is time of thinking of something new and which could make more sense to understand experiments. And then is what kind of things you can do if you don't think that collective motion is just something that is a continuous uninterrupted process. If you don't do that, I mean, eventually you can do many things. I mean, that the constraints imposed by assuming that they are all identical, that there is a democratic process, basically, that is a reciprocal kind of interactions, that they are exchanging velocity and so on. This is rather challenging all these assumptions and trying to see what kind of things you could do.
Okay, yeah, and you're right. I will add also, because I just talked about this tug of war type of also collective motions, that we have seen this in ants, for example, not only in cells.
Yes, sure. I mean, this kind of, they push, for example, one obstacle and many, and they may displace this, yes.
Okay, so Thomas in his first talk mentioned Vshape model as an example of non-equilibrium self-organization paradigm, and now Fernando, you showed us a sheep. From my very human perspective, sheep should graze optimally, yes, in an efficient way. So can one use your insight now into this organization of the flocking to make sheep better grazers?
Yes, in fact, this is not something, in fact, is going into the question of, okay, nice collective motion, but what the purpose of that, right? I mean, what can you do if you do this collective motion? And there is, I think, I hope I left that somewhere, but we were studying effectively how they consume, basically, they can not only explore, but exploit the surface where they move. And I was trying to find if I left, okay, I have not with me, I think, that slide, but yes, we studied that. So we studied how they consume, and we realized that their rates and I mean, you can tune the model in such a way that they do it, they exploit it in an optimal way. So they do optimal foraging, and the values that we observe for sheep seems to be in the region where it seems that quantity is optimized. What we were optimizing is the amount of grass they can take, assuming also that they have to optimize something else, which is someone should look for predators. If you put these two things in there, then you can optimize these rates, and seems to be close to what we measure. So the answer is yes.
So they operate in an optimal way, or you have to tune them?
No, they seem to operate in a natural, I mean, in an optimal way. But I mean, okay, if you try to do that, you have to say to optimize what, and if you just say, I want them to eat as much as possible, and you don't assume that there is any other constraint, you will obtain a solution. The solution is they should not do it together. So they should move away and find areas where the grass is available, and they should eat that, and that's it. However, if you say that there is predators, the guys will need, if they are alone, to be checking for the predator and going with the head up, and then they will waste, and they will spend most of the time trying avoiding being eaten instead of eating the grass. And
yeah. Thanks. Any more questions? If not, then the word to eat, which also tells us we are humans, so we have now got a lot of scientific food, but maybe we need a break and have a drink and something to eat. Unfortunately, I have no tequila at home, so I have to drink something differently. This is a very good time to thank all of you, the speakers and the people in the discussion. From the side of organizers, Josue and myself, I haven't spoken with Josue, but I think he's also happy with the result of this achievement. Yes, it's great and lots of new ideas, which we need to digest now with any sort of self-chosen drink or meal. I wish all of you a nice day, evening or night, depending on time zone. I hope I was politically correct in my wishes. And I think this is really a hope to meet one or the other in physical presence, as we call it here in Germany. Artificial is good for some purposes, but not for all purposes. Thanks a lot. Muchas gracias and goodbye.
Thank you, everyone.
Thank you.